Elon Musk has spent years convincing the world that Mars was humanity's ultimate destination. But now, almost overnight, that vision has shifted. The red planet is no longer the immediate priority. Instead, Musk is setting his sights somewhere much closer and far more strategic: the moon. But this isn't just about rockets or exploration. At the center of this sudden pivot is something far more unexpected: Tesla's humanoid robot, Optimus Gen 3. A machine Musk believes could become the first real worker on another world. The question is this the beginning of an off-world civilization, or a billion-dollar experiment destined to fail? For years, Elon Musk's roadmap sounded locked in. Mars was the target. The timelines were aggressive, the messaging was consistent, and every major SpaceX milestone felt like another step toward the red planet. But then, something shifted, and it didn't happen quietly. In a series of posts and replies that unfolded in less than 48 hours, Musk began talking less about Mars and more about the moon. Not as a side mission, not as a warm-up, but as the next major focus of his civilization strategy. To casual observers, it looked like a minor change in tone. But inside the space industry, it set off alarms. Because Musk doesn't pivot publicly unless something behind the scenes has already changed. For over a decade, Mars had been framed as humanity's insurance policy, a self-sustaining city capable of surviving even if Earth faced catastrophe. Musk repeated that vision in interviews, keynotes, and investor briefings. It became the philosophical backbone of SpaceX itself. So when he suddenly began describing the moon as the faster path to securing civilization, people started asking questions. Had Mars' timeline slipped again? Were Starship delays forcing a rethink? Or was this a calculated strategic move? Musk's explanation sounded simple on the surface. Building a self-sustaining presence on the moon, he argued, could realistically happen in under a decade. Mars, on the other hand, could take twice as long, maybe more. But the real story runs deeper than timelines. The shift reflects a growing sense of urgency in Musk's long-term thinking. Global instability, environmental risks, and technological threats have all reinforced his belief that humanity needs an off-world backup sooner rather than later. And waiting 20-plus years for Mars suddenly doesn't look fast enough. The moon offers something Mars can't: proximity. It's close enough for constant missions, rapid testing, and real-time problem-solving. If something breaks, you don't wait years to fix it. You send another mission within days. And that logistical advantage changes everything. Because once Musk reframed the moon not as a stepping stone, but as the first operational colony, it opened the door for entirely new technologies to debut there first. Technologies like Starship's heavy cargo systems, autonomous construction platforms, and most notably, Tesla's humanoid robot workforce. What started as a Mars support tool was suddenly repositioned as a lunar pioneer. And that's where the story takes a much more unexpected turn. When people imagine space colonization, Mars usually feels like the obvious choice. It's Earth-like in some ways. It has seasons, polar ice, even a day length close to ours. On paper, it sounds like the better long-term home. But when you strip away the romance and look purely at logistics, Mars becomes a nightmare. The biggest constraint is planetary alignment. Earth and Mars only line up for efficient travel once every 26 months. Miss that window, and you're waiting more than 2 years for the next shot. That means every mission has to go nearly perfectly, because there's no quick retry. And the journey itself? Brutal. A one-way trip to Mars takes roughly 6 months, sometimes longer depending on propulsion and orbital dynamics. During that time, spacecraft systems, cargo, and any onboard technology have to survive deep space radiation, micro-impacts, and complete isolation from Earth support. Now compare that to the moon. Launch windows open roughly every 10 days. Travel time, just about 48 hours. If something fails, engineers can diagnose the issue and send improved hardware almost immediately. That kind of rapid iteration is impossible with Mars. And iteration speed is everything. Space hardware rarely works perfectly on the first attempt. Systems fail. Materials degrade. Software behaves unpredictably in low gravity. The only way to refine technology is through repeated deployment, testing, and redesign. On Mars timelines, each learning cycle could take years. On the moon, it can happen in weeks. That difference alone transforms the moon into a live testing laboratory for civilization-scale infrastructure, life support systems, autonomous construction, resource extraction, energy grids. All of it can be trialed, broken, and improved far faster. There's also the communication factor. Signals between Earth and the Moon travel in just a few seconds. That enables near real-time control, supervision, and AI training feedback. Mars, by contrast, suffers delays ranging from 4 to 24 minutes, making real-time intervention impossible. For robotic operations, that latency gap is massive. It means the Moon can support supervised autonomy, where machines operate independently but still receive quick human guidance when needed. Mars requires full autonomy from day one, and that raises the technological bar dramatically. So when Musk evaluated where new systems, especially humanoid robots, could realistically be deployed first, the Moon became the obvious proving ground. Not because it's easier, but because it allows failure, learning, and scaling at a speed Mars simply can't match. And once that realization set in, Optimus was no longer just a Mars experiment. It was suddenly the key to making the Moon mission work at all. Long before the Moon pivot, Elon Musk had already made one thing clear. Humanoid robots would play a critical role in his off-world strategy. Optimus wasn't designed just to work in Tesla factories or help with logistics on Earth. From the beginning, Musk framed it as something much bigger, a machine built to go wherever humans couldn't. In earlier mission concepts, Optimus was slated to travel to Mars alongside the first Starship flights, not as cargo, but as part of a simulated crew. The idea was simple but powerful. Before risking human lives, send humanoid robots to do the dangerous groundwork. Site scouting, terrain analysis, infrastructure prep. Tasks that would normally require astronauts could be handled by machines that don't need oxygen, don't panic under pressure, and don't require a return ticket home. Musk even described Optimus as a versatile workforce, capable of constructing the earliest layers of a Martian settlement, setting up solar arrays, assembling habitats, transporting materials across hostile terrain, all before the first human ever steps foot on the planet. That vision reframed colonization entirely. Instead of humans building cities from scratch, robots would prepare everything in advance, turning Mars missions from survival challenges into arrival procedures. But when the Moon suddenly moved to the top of Musk's priority list, Optimus' role didn't shrink. It expanded, because the lunar environment offers something Mars can't in the short term, a nearby proving ground where humanoid robotics can be tested under real space conditions. If Optimus can function on the Moon, operating tools, assembling structures, navigating dust-heavy terrain, it validates the entire robotic workforce model. It proves machines can handle extraterrestrial labor, and that proof is essential before scaling to Mars. There's also the transportation factor. Early Starship missions will prioritize cargo efficiency. Sending humans requires life support, safety redundancies, and enormous cost overhead. Robots, by contrast, are simpler payloads. They can be powered down during transit. They don't need food, water, or psychological support. And if one fails, the mission continues. That cold efficiency makes Optimus an ideal first mover. It transforms space deployment from fragile human exploration into scalable industrial expansion, which is exactly why Musk began repositioning Optimus not as a factory assistant, but as humanity's first off-world labor force. But ambition alone isn't enough, because operating on the Moon demands far more than vision. It requires technology capable of surviving one of the harshest environments in the solar system. And that raises the next question. Is Optimus Gen 3 actually built for that reality? Or is it still just a prototype with good marketing? On the surface, Tesla's Optimus might look like just another humanoid robot, sleek frame, human height, mechanical hands. But Gen 3 is where the project starts shifting from experimental prototype to something far more operational. Because under that humanoid shell sits the same AI philosophy that powers Tesla's autonomous vehicles, an end-to-end neural network system designed to interpret the world visually and act in real time. At the core of Optimus Gen 3 is Tesla's AI-5 chip, with future upgrades like AI-6 and AI-7 already in development. These chips aren't just incremental improvements. They're designed to massively expand processing power, enabling the robot to interpret complex environments, adapt to new terrain, and make decisions without constant human input. That autonomy is critical in space. Unlike traditional exploration robots that rely heavily on pre-programmed instructions, Optimus is trained using imitation learning. It watches humans perform tasks, lifting objects, assembling components, using tools, and translates that visual data into executable behavior. In simple terms, it learns the way humans do. And that learning model becomes extremely valuable in unpredictable environments like the moon, where you can't possibly pre-program every scenario a robot might encounter. Physically, Gen 3 also represents a major leap. Standing around 5 foot 11 inches tall, Optimus is built to human scale. That might sound trivial, but it's a massive strategic advantage. Tools, habitats, vehicles, and infrastructure designed for astronauts can also be used by the robot, eliminating the need to redesign equipment for specialized machines. Then there are the hands. Earlier versions featured around 11 degrees of freedom. Gen 3 reportedly doubles that to 22, enabling far more precise manipulation. That means gripping tools, fastening bolts, handling delicate components, even assembling structural frameworks becomes realistically possible. Tactile sensors add another layer, giving the robot pressure feedback similar to human touch. It can gauge grip strength, adjust force, and avoid damaging fragile equipment. Mobility is another key upgrade. Demo footage has already shown Optimus walking across uneven terrain, climbing steps, and stabilizing itself while carrying loads. It's not fast yet, but speed isn't the priority. Stability and adaptability are. And unlike wheeled rovers, which struggle on steep slopes or jagged rock formations, a bipedal system can step over obstacles, navigate tight structures, and operate inside human-built environments. Navigation itself relies entirely on vision. GPS doesn't exist on the moon, but Optimus uses camera-based perception, semantic segmentation, depth mapping, and object recognition to understand its surroundings. It can identify hazards, map terrain, and plan movement paths without satellite positioning. In essence, it sees, thinks, and moves, all powered by neural networks trained on billions of miles of real-world Tesla driving data, repurposed into robotic spatial intelligence. On paper, that combination makes Optimus Gen 3 uniquely suited for extraterrestrial deployment. It can learn new tasks, use human tools, adapt to unfamiliar terrain, and operate with increasing independence the longer it's deployed. But capability alone doesn't guarantee success, because the moon isn't just another job site. It's an unforgiving, hostile environment that destroys unprotected technology faster than almost anywhere else in space. And that's where the real test begins. If Optimus Gen 3 does make it to the lunar surface, it won't be going there as a symbolic passenger. Musk's vision positions the robot as an active worker, part of an early robotic workforce designed to prepare the moon for long-term human presence. And the task list is far more practical than people might expect. One of the first roles Optimus could take on is cargo handling. Every Starship mission will land with massive payloads, equipment, structural components, power systems, scientific instruments. Unloading that cargo manually would require astronauts performing risky spacewalks in bulky EVA suits. Optimus changes that equation completely. A humanoid robot can step directly onto the surface, remove payloads, transport them, and stage materials for assembly, all without exposing humans to danger. And since it doesn't require life support, it can operate for extended periods with minimal oversight. From there, construction becomes the next logical step. Optimus could assemble modular habitats, connect structural panels, deploy solar arrays, and set up early infrastructure grids. Tasks that are repetitive, physically demanding, and time-consuming for astronauts become scalable when handled by machines. And that scalability is key. Instead of sending a few robots, Musk's long-term model involves deploying entire teams. Swarm-style coordination, where multiple Optimus units work simultaneously, dividing workloads and accelerating build timelines dramatically. Imagine one group assembling habitat frames, another installing power systems, while others transport materials from landing zones, all operating in synchronized workflows. Resource scouting is another major function. Using onboard cameras and AI-driven terrain mapping, Optimus could survey the lunar surface, identifying mineral deposits, structural cave systems, or subsurface ice, one of the most valuable resources for sustaining human life off-world. Water ice can be converted into drinking water, breathable oxygen, and even rocket fuel. Finding stable reserves would be a cornerstone milestone for any permanent lunar base. And unlike traditional rovers, Optimus can physically interact with its environment, collecting samples, drilling surfaces, or deploying sensors in difficult terrain. Mobility also opens new mission profiles. It could transport tools between sites, move equipment into shadowed craters, or assist in building underground shelters inside lava tubes, natural formations that provide radiation shielding. Then there's autonomous logistics. With Tesla's Dojo supercomputer processing operational data back on Earth, Optimus units could continuously improve their performance. Tasks completed on the Moon feed training models, which then update behavior across the entire robotic fleet. And because communication delay between Earth and the Moon is only a few seconds, engineers can supervise operations in near real time, stepping in only when decisions become too complex for AI alone. This supervised autonomy model dramatically reduces mission risk while preserving robotic independence. Over time, Optimus wouldn't just execute tasks. It would learn, optimize, and refine lunar operations faster than any human workforce could. But for all this potential, there's a harsh reality that every space technology eventually collides with. The Moon doesn't care how advanced your AI is. Extreme temperatures, radiation, and abrasive dust have destroyed far simpler machines in the past. And surviving those conditions may be the single greatest obstacle standing between Optimus and becoming humanity's first true off-world worker. At its core, Elon Musk's vision isn't really about the Moon, and it never was. The lunar surface is just the testing ground, a harsh, unforgiving laboratory where humanity learns whether its machines can truly survive beyond Earth. And Optimus Gen 3 sits right at the center of that experiment. If it works, the implications are enormous. A successful humanoid workforce on the Moon would validate an entirely new model of space expansion, one where robots arrive first, build first, and prepare entire worlds before humans ever set foot there. Habitats assembled, power grids deployed, resources mapped, risks reduced. Mars would no longer feel impossibly distant, just the next construction site. But if it fails, the consequences go beyond one robot. It would expose the limits of current AI autonomy, the fragility of humanoid mechanics in extraterrestrial environments, the gap between ambitious timelines and operational reality. And it could delay Musk's multi-planetary roadmap by years. Because sending robots to space isn't the hard part. Keeping them operational, productive, and economically viable is where the real battle begins. Still, Musk has never been known for playing it safe. From reusable rockets to mass-produced EVs, his strategy has always followed the same pattern: deploy early, iterate fast, scale aggressively. And the Moon offers the perfect proving ground for that philosophy. Close enough to test quickly, harsh enough to prove durability, strategic enough to matter. So whether Optimus becomes the first true off-world worker or the most expensive prototype ever launched, one thing is certain. The mission itself marks a turning point. Because the moment humanoid robots begin working on another world, space exploration stops being exploration and starts becoming industry.